Hello and welcome to our second video exploring exoplanet detection in the celestial mechanics section. Last video we talked about the historical origins of Kepler's laws, but today we're going to be taking a deep dive into the mathematical origins of those laws. Using Newton's laws, we're going to formally derive Kepler's laws from first principles, and this will be split over two videos. Now this derivation isn't something exoplaneteers regularly use, but anyone interested in planetary dynamics will certainly want to have a good handle on this. Now obviously, because this is a mathematical derivation, we are going to be diving into some equations today. A prerequisite for the derivation I'm going to show you will be vector calculus, so hopefully you've been exposed to that before. My advice is go at your own pace today and pause the video as much as needed. As stated, we will be starting from Newton's laws, which were first described in his magnum opus Principia in 1687. Newton was of course absolutely brilliant, but he was also a flawed character. He famously courted controversy with both Robert Hooke regarding the discovery of the inverse square law, and also Gottfried Leibniz regarding the invention of calculus. We often romanticize that science advances through individual brilliant scientists working in isolation, but even in the case of Isaac Newton, his work was a product of thinking of the day. At a minimum, he was influenced by his peers, and Hooke would argue that he actually plagiarized some of them. Regardless, Newton presented an indisputably deep, accurate, and comprehensive understanding of the orbits that far exceeded anything previously published. And so, we will begin with the laws which are credited to him today. For our derivation, we're going to follow the chapter Murray and Crayer 2010 from the textbook Exoplanets, and I'll link down below for a full version. Let me just inject a brief aside on notation. Any symbols which are emboldened denote a vector, whereas any symbols which are unboldened denote a scalar. If you see a little hat on top of a vector, that means it's a unit vector, and if you ever see a vector with two modulus symbols around it, that denotes that this is the magnitude of that vector. Here's our basic setup. We have two massive bodies, labeled 1 and 2, at arbitrary positions relative to an origin, denoted by the position vectors r1 and r2. Let's define r12 as the position vector from 1 to 2. So, walking along the vectors, we can see that r12 equals minus r1 plus r2. Now let's write down Newton's universal law of gravitation in vector form, where here I'm defining F21 as the force applied on 2 by 1. Note that because of that minus sign, this is a force acting in the opposite direction to that of the r12 vector, which is of course because gravity is an attractive force. Check your understanding by rewriting in terms of r21 and or F12. Finally, before moving on, I'm going to use r rather than r12 simply for notational convenience in what follows. Now, along with the universal law of gravitation, we're going to use Newton's second law, which describes how an object's acceleration is proportional to the force applied to it. Notice how we write this as r dot dot, where each dot represents a time derivative. So velocity would be dr dt, or r dot, and acceleration is dv dt, or r dot dot. Let's now equate these two to get the response of each object. So the force applied on 2 by 1 causes 2 to accelerate, which we denote as r2 dot dot. And we know what this force is. It's already written in the top left green box. Thus we can say, as we've already said, that the negative sign here implies that F21 is a force applied in the opposite direction to the vector r. Doing the same for F12, the sign changes now because r equals r21, which equals minus r12, and that minus sign cancels out with the previous minus. Now let's get into what we really want, which is how the r vector changes over time. Using these results, we can write the following differential equation. Okay, let's take this equation over to a clean slide and take a vector product of r with it. The last term disappears since a vector self-product is 0, And this just leaves us with a simple expression that r cross r dot dot equals 0. To go further, we have to use some vector calculus rules. In particular, we'll use the fact that the derivative of a vector product follows the chain rule, as shown here. So if we write a equals r and b equals r dot, then we get another self-product which goes to 0, and then we recover the r cross r dot dot term. So this means that since r cross r dot dot equals 0, then the derivative of r cross r dot must equal 0 too. And we can just integrate that with respect to time to obtain this key result, where h here is a non-time evolving vector, and I'm going to stick a box around this because it's so important. Okay, but why is this important, you might well ask? Well, it tells us a couple of things. First, it reveals that the motion of the planet with respect to the star lies in a plane which is perpendicular to the direction of h due to the nature of the vector product. It also means that the position and velocity vectors always lie in the same plane, and we call this plane the orbital plane. This h vector therefore lies along the direction of the angular momentum vector, and is thus called exactly that. Now, we haven't derived any of Kepler's laws just yet, but this is a very important result, because it tells us that the motion of two massive bodies under gravity lies within a flat plane. Now, Kepler never wrote that down as a law, perhaps because Ptolemy had long been assuming it, and of course we sort of knew this from looking at the ecliptic plane, but we can imagine this being like Kepler's Zeroth law, and we now have found a natural explanation as to why this is so. It's actually now pretty easy to get to Kepler's second law from this result. To achieve this, we're going to write out r and r dot in polar coordinates. To save time, I'm not going to derive this here, but this is a standard vector calculus result which you can find in any good textbook on the subject, or even over here at this Wikipedia link that I'll put down in the description. Let's take our equation in the orange box, often called the angular momentum integral, and substitute it into the r dot expansion. As we did earlier, we can simply drop any vector self-product terms. And now let's group up all of the scalar terms together on one side. The r and h vectors can be written as their magnitude multiplied by their unit vectors. This reveals the following, where we note that since the r and theta unit vectors lie in the orbital plane, then their vector product must be normal to both, and therefore point in the same direction as h. And so, we can write that the magnitude of the h vector is the planet-star separation squared multiplied by theta dot. Okay, we're almost there. To finish, we just need to think like Kepler did. Kepler's second law talks about the area swept out. So, let's write out the infinitesimal area element, dA, equals the radial integral of r theta to give 1/2 r squared d theta. I like to think of this like the area of an infinitesimal triangle, which is a half base times by height, whereas here the height is r and the base is the arc length r d theta. Finally now, dividing both sides by dt, we get a dot on the left hand side and the expression we just derived on the right. Since h is a constant, then this means that dA dt is a constant. In other words, planets sweep out equal areas over equal intervals. Kepler's second law. Okay, I think that's a good point to stop and catch our breath, and in the next video we'll turn to the first and third laws. Try working through the derivation today by yourself and look at all of those vectors, make sure the directions of them all make sense to you. Of course, if you have any questions about anything in this video, please be sure to add it down below in the comments and I'll do my best to get back to you. And as always, thank you for watching.